got an interesting triple integral problem today. I don't know if interesting is the right word. I certainly find it interesting, and I think it's fun, but that's a discussion for another time. So here's our triple integral problem for the day. I want to find the volume of a hemisphere with a radius of 3. And I want to set up a single integral, a double integral, and a triple integral to represent the same volume. So for the single integral, we're going to drop ourselves back to Calc 2 when we were slicing things up, but we only got to use one variable. So let's remind ourselves how to do that problem. Let's remind ourselves what we had to do that problem real quick and set up that integral. Then let's think about a double integral. And then let's set up a triple integral. All right, here we go. So if you would recall, if we set the Wayback Machine to Calc 2, when we were setting up integrals and we wanted to find the volume of the hemisphere. Now remember, we already know what the volume of the hemisphere is. It's going to be 4/3 pi r cubed. So we already know that this is 4 times pi, 36 pi, divided by 2. So 18 pi. So we already know what the answer is. That's the reason that I picked hemisphere, so that we would see that our single integral would give us the value that we wanted, our double integral would give the same value, and our triple integral would give it the same value. Let's recall what we need to do to find the volume of a hemisphere, radius 3, using a single integral. So thinking back to Calc, we only got to use Calc 2, we only got to use one variable at the time. And so what we did, I don't want to set this up as a quiz or anything like that, but what we did was we set up a slice . We set up a slice and gave that the delta variable. The thinness of this slice, let's say, is the delta H. And then we said, if this is a piece of a hemisphere, then the volume of that slice is pi r squared times the height. So for that single integral, we set up a volume of the slice as pi times the radius squared times the height. So the radius is going to be the radius of just this part here up to where the slice touches the hemisphere. That's going to be our radius. What we need to do is write the radius in terms of some vertical variable, h. And h can be the height of this slice above the base of our hemisphere. This is just a recall this, so I'm just going to write down what we did. What we did was we set up a right triangle to get a relationship between the r and the h. What we needed to do was find a relationship between r and h so I can write the volume of the slice in terms of one variable, because we only get to use one variable. So we set up this right triangle where the hypotenuse was the radius of the hemisphere. The height of the triangle was h, and the base of the triangle was r. So we have this triangle with a hypotenuse, this right triangle with a hypotenuse of 3, vertical leg h, horizontal leg r. And this gave us a relationship between r and h. So this tells us that r squared plus h squared equals 3 squared. And so r is the square root of 9 minus h squared. That goes in for our radius. R is the square root of 9 minus h squared. That gets squared, and then the height of this cylinder, this little slice, is delta H. Now we just need to add up all the volume of all such slices. We're imagining this hemisphere as a stack of cylinders, and those cylinders are getting super thin. It's kind of like 3D printing, and then you drop down to like a finer nozzle. I don't have a 3D printer, so I don't know what you call the parts. But the part that squirts the plastic onto the model that you're making, that just gets smaller. And so we just need to add up all the values of H. So H at the bottom is add up the volumes of the slices, where volumes, add up the slices where we're in. I lost that sentence partway through. We're going to integrate from 0 to 3, because the lowest slice is down here at the base of our hemisphere when H is equal to 0. And the top slice is here at the top of our hemisphere when H is equal to 3. We integrate where there is a slice. So the total, after we add up all such slices, I'm going to factor out the pi. We're going to integrate, and I'm going to simplify 9 minus h squared, the square root of 9 minus h squared squared, to just be 9 minus h squared. The discrete delta h becomes a continuous dh, and we integrate over all the values of h from 0 to 3. Any questions? So we just got to sort out this integral, and some stuff happens, and we should get 18 pi for the volume of our hemisphere. Any questions? I'm going to cheat a little bit. This is just a recall. All right. So in this case, we got our volume. The delta H was the height, and we got a volume because we had pi times the radius squared. So we found the volume of each of these slices. So there's a single integral that gives us the volume of a hemisphere. Now, this was useful over just 4/3 pi r cubed, cut in half, in case there was something variable about this hemisphere. So a common problem would be to vary the density, but because we only got to use one variable that was going up and down like this, that was the only direction that we could vary the density. We could say the density at any point above the base is given by, and then some function of the height above the base. Because we have to write everything in terms of one variable, that is the restriction of writing an integral with a single variable. Everything has to be in terms of that one variable. If the hemisphere had a variable density that was changing from left to right, all of a sudden single variable calculus has to tap out. Unless actually we could just write slices going the other direction. We would have to write slices going in the h direction. Sorry, in the horizontal direction. If the density is changing side to side, then our slices will have to be cut side to side. So they'll at least still have the shape of these semicircles, but we'd have a different expression for the volume. Or if we're throwing density into it, a different expression for the mass. Everything has to go in one direction. If our density varies up and down, then our variable, we have to integrate up and down. If our density varies left and right, then we have to integrate left and right. let's switch over to a double integral. So we can use a double integral by calculating by thinking of the double integral as calculating the volume under a surface and above a region. So a double integral it's going to be the volume under a surface and above a region. The surface will be some function of x and y. And the region over which we integrate will be just called R. So in this case, we're going to imagine the hemisphere as being the volume underneath a surface, f of x and y, and above a region R in the xy plane. So let's think about that. What we're going to have is we're going to have the base is going to be a circle in the xy plane. Spelled y wrong. And z will be some height above the xy plane. So there's a hemisphere above a circle. So what we're going to do is integrate the function. We're going to write z as a function of x and y, and then we're going to integrate that over the region R, which is just going to be a circle of radius 3 in the xy plane. So we need to do two things. We need to find a function for our hemisphere, and then we need to find an equation for our circle. Then we need to set up a couple of double integrals because we always set up two. So the hemisphere, or the sphere in x, y, and z will be x squared plus y squared plus z squared equals 3 squared. And we're just going to solve that for z because that gives us all a function for the 6 different hemispheres that we can pull out of that the sphere. So x squared plus y squared plus z squared equals 3 squared. That's going to be a sphere of radius 3 centered at the origin. And I want this top part. I think of the positive x as the front and the back, the positive y as the right, and the negative y as the left. Positive z will be the top, negative z will be the bottom. So the top part of the sphere, so the x squared plus y squared plus z squared equals 3 squared is a sphere. If I solve this for z, that'll give us the top hemisphere. The positive square roots of 9 minus x squared minus y squared. So the z equals the square root of 9 minus x squared minus y squared can be the top hemisphere, where the negative square root, z equals negative square root will be the bottom. X equals positive square root will be the front. X equals negative square root will be the back. Y equals positive square root will be the right. Y equals negative square root will be the left. Once I started doing the others, I had to do all 6. So this is the function that we're going to integrate. That's the surface. Now we need to describe the region R for a double integral. So we're setting up a region. We're integrating over a region R, our height function. But what we need to do is describe the region R in the XY plane. So draw the circle first. So the region is just the circle x squared plus y squared equals 3 squared. Now we're setting up a double integral. So I need to say what x is between and what's y between. So I can either think of this circle as y as a function of x, or two functions of x, plus or minus the square root of 9 minus x squared, or I can write x as a function of y, plus or minus the square root of 9 minus y squared. So we have got a couple of double integrals that we can write. The last double integral, the outside one, always has to be for constants. So if we set up a dx dy integral where y goes second, I set this up dx dy. So I can either set this up as a dx dy integral or as a dy dx integral. Oh, I did it exactly backwards. So in this case, with a double integral, we're thinking volume below a surface and above a region. The last integral that happens, the one on the outside, always has to be between constants. We have to describe the y values between constants. The lowest y value on this circle is -3, and the largest y value is -3. So the y's will integrate from -3 to 3. And then for the x's, since we're integrating the whole circle, we'll use x is plus and minus the square root of 9 minus y squared. So the lowest value is going to be negative square root of 9 minus y squared, and the largest value will be positive square root of 9 minus y squared. Or we could set it up the other direction, dy dx. It's a symmetric problem, so it doesn't matter in this case. So the x's will go from -3 to 3. And the y will go from negative square roots to positive square roots. Now, if we only wanted part of the hemisphere, if we only wanted the front half of the hemisphere where x's are positive, then we could instead integrate x from 0 to 3. Or we could integrate x from 0 to the square root to positive square root of 9 minus y squared. But what we had to do was figure out, had to tell the integral what values of x to plug in and what values of y to plug in. Just like in the single variable integral, we had to tell the integral what values of h to plug in. And what we're doing is calculating this height at all these different coordinates, x and y. Whereas in the single variable integral, we're calculating this volume at all these different heights. Any questions? So right now we're looking at this integral, and you're wondering if I'm going to calculate it for you. And since I just said that, you could probably figure out that the answer is going to be no. But to give you a start, mainly because it's trigonometric substitution, because we got the square root of 9 minus y squared is the first thing that we're trying to integrate. Actually, 9 minus x squared minus y squared. So right now, gosh, I hope this works out to 18 pi. But in the middle there is going to be some messy parts. That's where I got my y's from for the second one. So this part right here, I would recommend, if you want to do this integral, try some trig substitution. Y needs to be something, some function of theta. The constant is 9 minus x squared. We know it's trig substitution because it's the form. We've got the square root of a constant minus y squared. It's also a sine trig sub, because the structure of this function is the square root of a squared minus y squared. And so y is going to be a sine theta. That's the substitution that you're going to want to make. Because the a squared minus y squared will turn into a squared minus a squared sine theta, and that can turn into a cosine squared. It has been a while, which is why I just filled it in with ... and said, let's find out who's interested in this. For the most part, once you get to this part of the problem, we're in the we'll just take your word for it, Leach category, which is, just as a side note, way too much power to give to me. All right, for a triple integral, instead of thinking of where you're going to use a triple integral to calculate volume, and it works differently. For a triple integral to calculate volume, we need to describe the solid W. Do we use W? I think we use W. If not, we're using W now. And we just need to integrate the function 1. So for a triple integral to calculate volume, we just integrate over some solid W, the function 1 dV is the, and that'll give us the volume of the solid W. So I don't need to actually integrate a function, well, until I start doing the integration. We don't need a function to represent the height above a point in the XY plane, and we don't need the function to involve the volume of a slice. We just need to integrate the function 1. Just like the integral, the double integral of 1 over some region will give you the area of the region, just like a single integral of the function 1 over an interval will give you the length of the interval. So now, instead of coming up with a function that we're going to integrate, we're going to describe the hemisphere with a triple integral. What's x between, what's y between, what's z between. So we're going to have our hemisphere oops, I usually put y there. I think that's the tradition. So our hemisphere is still the top half of the sphere x squared plus y squared plus z squared. Equals 3 squared. But we're now going to describe this with a dx, dy, dz, and actually I'm going to use a dz, dy, dx. We're going to say, we're just going to describe the solid in the triple integral. What's x between, what's y between, what's z between. So our integral of the function 1 dv is going to be a triple integral. What's x between? What's y between? And what's z between? But instead of integrating some funky function, we're just integrating the function 1 because we're going after a volume. And I've set my dv up as a dx, dy, dz. Nope, I've set it up as a dz, dy, dx. I always think of them going the other direction. So this is a dz, dy, dx. And we're just going to be thinking about what's z between, what's y between, what's x between. The z, the endpoint, the interval for z can involve x and y. The early integrals can be functions of the upcoming variables. Once I've integrated dz, my y integral can be functions of x, and then my x integral has to be constants. So let's start there with the constants. If we look at this hemisphere, the lowest x value is going to be a -3, and the highest x value is going to be 3. So we'll integrate on the x's from -3 to 3. Those are always the easiest ones to pick out. We're not worried about the curviness of the hemisphere. We just need to say the x values go between -3 and 3. Now I'm actually going to jump to my dz because I'm cheating by doing the easiest one. I think about what values of the values of z. The lowest value of z is going to be 0. That's sitting on the xy plane. We need to go from the lowest value of z to the highest value of z. And at any point xy, the highest value of z is going to be the top of our hemisphere. So we're still integrating this function. I need to write z as a function of x and y. And now I need to just describe the y values for all these different values of x. So the bottom is going to be 0, the xy plane. The top half will be the top of the on the hemisphere. So now I need to describe the y's. And at this point, you can see how I super cheated on this problem. Because by integrating from 0 to the function square root of 9 minus x squared minus y squared, if we integrate 1 dz, we just get z, and then we plug in from 0 to this top function. So that just gives us the same y that we had before, from negative square root of 9 minus x squared to positive square root of 9 minus x squared. Oops. 3 squared, not cubed. Y is not going from -3 to 3 because we need to capture the curviness of the region. So if we look at this from the top down, if we look at the circle from the top down, x is going between 3 and 3. If we integrate just y between 3 and 3, then we're just going to get a rectangle. So if we said that x goes between just -3 and 3, if we just put y, so that says x is between -3 and 3. If we just put y equals -3 and 3, then we're just going to make a box. And it would be this rectangle, but we don't want a rectangle. We don't want to go from y equals -3 to y equals +3. That would give us this whole square. We want the top to be this curvy part and the bottom to be the curvy part. This strategy is the same strategy that we had when we were setting up double integrals. In double integrals, we just said what's x between and what's y between. So now in this triple integral, we're just setting up what's x between, what's y between, and what's z between. Now, in each of these cases, we were just calculating a volume because we were focused on setting up the integrals, not about actually finding the volume of the hemisphere, because we knew that before we started any of this calculus business. Before integrals even walked into the room, we already knew the answer was going to be 18 pi. Because 18 pi was not the point, setting up the integrals was the point. Now, it could be that we're not just calculating the volume of this hemisphere, but suppose that this hemisphere has a variable density. I'm just going to lean back on that. In a single variable, we had to integrate in whatever direction the density was changing. If the density was different at any point x, y, then all of a sudden we would at least need a double integral. We would need to write the mass. If the density is varying at any point x and y, I need to be able to capture the variable density by plugging in different values of x and y, because that's what this integral is doing, just plugging in different values of x and y. So if my density is variable at different points x and y, then I need to use a double integral. However, if my density is variable at any points x, y, and z, now instead of just integrating the function 1, I have to say these are the values of x, y, and z that we're plugging in, and then I'll put my density function here. And I'll integrate my density function to find the mass of my hemisphere. Any questions? So a lot of times we get hung up on the calculation so much that we just think, why are we spending all this effort to calculate the volume of this hemisphere? The volume of the hemisphere is not the point. Thinking about triple integrals is the point. And it's a simple idea. What values of x, y, and z are we plugging into the function? That's what the integral is asking. Plug in these values of x, y, and z. In a double integral, plug in these values of x. Plug in these values of x and y. In a single integral, plug in these values of h. That's what the integral is doing. It's just plugging in a bunch of values for the function and then adding things up. That's the thinking that goes behind this. Since the question is no longer, why are we calculating this volume if we already know it? The natural question would be, where can I apply this kind of thinking in my future career as a fill in the blank? And the honest answer is, I don't know, because I'm not allowed to look into the future and determine what your future career is. I'm not allowed to look into the future and fill in that blank for you. So I hate to pass the buck on you, but how you use this knowledge is going to be up to you. Oh, I've also been required to say that I am actually not capable of looking into the future. I forgot, if I record the part where it says I'm not allowed to, I have to say it's because I'm not able to. They told me I had to say that. It's because they're all watching, and once I tell you, then it changes. So they're like, "Oh, dude, stop changing stuff." I just get all these emails, like every single one. Then I'm down in HR, and it's a whole big thing. You know what I mean? That's right. Got to maintain the sacred timeline. We don't want any variance. All right. So the next thing that we need to do, now that we're super experts in triple integrals, having spent, like 2 days on it, is to change up the types of coordinates that we can use, because all we're doing is describing stuff in 3 dimensions. And in this case, we've used coordinates x, y, and z, rectangular coordinates. But there are other kinds of coordinates. In 2 dimensions, they're polar coordinates, r and theta. In 3 dimensions, we have rectangular coordinates. We also have cylindrical coordinates, and we also have spherical coordinates. It's just different ways of describing points in 3-dimensional space. And that's all we're doing when we're setting up a triple integral, is describing a bunch of points in 3-dimensional space and saying, plug this set of points into this function. W is just a bunch of points x, y, and z that we're plugging into this function 1, multiplying by the dv that gets infinitely small, and then just adding up the values of this function. Any questions? All right. So one of the reasons that I'm not allowed to look into your future is the way that I do it. I don't just sit here and look. It's not like a video. I actually travel up, I take a look around, and then I come back. And they're like, oh, dude, you're not allowed to do that anymore. It's messing stuff up. It's even worse when I go back and then come forward. But the funny part is, when I go back and come forward, it's only me and the watchers who sit outside of time that can see all the changes that happened. No one else can tell. Because if I go back and change your history, then it just, you don't remember. I go back to a time where you don't remember your last 5 years. And it's just a different 5 years. You know what I mean? All right. All right, that's going to do it for today. Tomorrow, we're going to talk about different kinds of coordinates. So it's going to be extra uncomfortable because you might be shaky on setting up double integrals and triple integrals. And then we're going to start doing this in a different language. We're going to use separate coordinates, a different set of coordinates. So that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.